Hi everyone, and welcome back to Fundamentals of Engineering with Farah, Mechanics of Materials, Strain Energy. In last video, we reviewed the strain energy stored in a variable cross-section like in a tapered cone when a concentrated load of P applied at the smaller cross-sectional area. And this time we want to see if we just have like a similar problem, but this time we use a stepped cone by, for example, in our case, five cylinders with the same length, and then calculate the strain energy function, and then make a comparison between the previous condition. So each of this part is equal to this identical length of L over 5, and the radius is increasing like in a small increment. So for example, in our case, we have like A1 through A5, and then our radius is increasing from, at the beginning, we call it like R1, and then 1.1, 1.3, 1.5, 1.7, and 1.9. That's our five pieces. Then strain energy comes from U. Capital U is equal to summation of sigma I squared times length of that part over 2 modulus of elasticity times area of that section. So in such case, if we have uh, our equation written like replace sigma by force over the area, and then get the get the some part out of the variable like r, so p squared times length of each part, which is L over 5, then times 2 modulo of elasticity, and area is just, if we just in brackets jot down all the areas based off the smallest one, which is pi times r1 squared. So definitely the first one is 1 over 1.1 r1 squared plus 1 over 1.3 squared, all the way to 1 over 1.9 squared, and then definitely pi r1 squared is a stand for the minimum cross section, which we call the a submin, and the numeric value in the bracket is just equal to numeric value of 2.4856. If you do the math and jot down everything based off pi squared times L over 4 times EA minimum, you will reach to a numeric value of 0.99, which shows our percentage of error is less than 10% in when we are using the stepped cone in comparison to tapered cone. So if you have a closer look to my bad, if you have a closer look to a stepped cone, it just gives you a strain energy function is equal to 99% of pi squared times L over 4 EA minimum. And when you use the tapered cone, like in our previous problem, U is equal to pi squared L times 4 times modulus of elasticity times area minimum. This is like numeric value of 1, and this is like numeric value of 99. So it just says the percentage of error is like 0.6%, 0.6%, or 0.006. If you it was just like you can easily see how the result is close when we use a much simpler function like a stepped cone in versus like avoid the integration of the problem. You can see how close the result are, and then it just when we have like five using five element, if you increase it like to 10 to 50 to 60 to 100, it just says you can almost replace your problem with cylinders with the same length, and then as you increase the number of the cylinders you get much more close to the real integration function. Thank you. Will solve more problems in energy strain energy calculation.